So let's say we are given a cantilever, on a cantilever, we are given a uniformly distributed load. That is a U.D.L load of W per unit on this particular case. And we are asked to draw the shearing force and the bending moment diagram. That is, we are asked to calculate the shearing force and the bending moment in order to draw the diagrams. This is how we are going to do it. So now, if we are to calculate the shearing force at point A here, the shearing force of a uniformly distributed load is the load times the distance at which the load is being applied. So now we have the uniform distributed load at A, which is the shearing force. The shearing force at A is given by minus the load times the entire distance. But you see, at this point, A is not moving at all. There is no bending that is applied. So it's going to be minus W times 0, which will be equals to 0 kilo Newton. That is for the uniformly distributed load. But if we are asked to find for the uniformly distributed load at the section X here, the uniformly distributed the shearing force at X is equals to the load here, which is minus W times the distance from A. The distance from here to here is given by X. So we have minus W times X. And that is the shearing force of this. Then the shearing force at point B, the shearing force at point B is equals to minus the load here times the total distance, which is minus W times A. Everything is given by kilonewton, kilonewton, so that's in form of Newton. But it is mostly given in form of kilonewton and stuff like that. So now, since we have gotten our shearing force, now how do we find for our bending moment? Now earlier I explained that our bending moment is the multiplication of our force times the distance from the centroid. So if we are asked to find for our bending moment at A is going to be 0, because the shearing force times the distance here is going to be 0. So let's say that the bending moment at A is equals to 0, just 0 kilonewton per meter. But now the shearing force at X. So now let me give you a little bit of explanation. Let's say that this section X here, this is it here. We have XX. Then we have our beam here. Our distance here is X from here to here. We have that uniform distributed load here, and this is our point A. So now if this is what we get here, if I ask to find for our bending moment, we will first have to calculate the shearing force, which is the W per unit run. Then after calculating the W per unit run, we get our shearing force as W times X. We get our shearing force at W times X. After getting our shearing force at W times X, then we have to find for the centroid. Now the way to find for the centroid is to imagine that this load is in form of a box. So let's say our load here is in form of a rectangular form, something like this. This is how the load is. So the centroid of a rectangle, it will be this total length divided by 2. That is x over 2. That is where the centroid is. Imagine that we have a rectangle like this. The place where we can balance a pivot, that would be the center. The place where we can balance something like this would be at the middle, which is half of the entire distance. The place where we can balance this type of triangle will be at the middle. So therefore, the centroid is at x over 2. So now the bending moment would be the shearing force times the distance from the centroid. So let us look at it this way. So let's say we have found the shearing force. So we are going to imagine that we are having a point load at the center of the uniformly distributed load. So this uniformly distributed load, then after finding the shearing force, we imagine we have a point load at this point, and this point here is equals to x over 2 distance. That is this distance here divided by 2. So this one here is the shearing force, which is W times X. Then our bending moment here, our bending moment at this point here will be equals to WX times this distance from here to here, which is x over 2 times x over 2, which is equals to w x squared over 2. So that is how our bending moment is being found. So therefore, our bending moment at x will be equals to minus w x squared over 2. So that is how that is our bending moment. Then if we are our bending moment at the last point b here, our bending moment at b would be equals to the same thing. We have our shearing force to be minus wl times the distance from the center, that is the center of L, which is L over 2. That is times L over 2, which is equals to minus WL squared all over 2 in kilonewton meter. Kilonewton meter. So now these are the values, these are the formulas for finding the bending moment and the shearing force of a unit pump. Now to the diagram. For the shearing force, let's say we have a neutral of 0, 0 here. So the shearing force at A here is 0. Then the shearing force at X here is W times X. Let me put it this way. The shearing force at here is W times X. We have it here. We have WX, and the shearing force here is WA. Everything is negative. That is the shearing force. So this is the shearing force diagram. Then for the bending moment diagram, the bending moment at A here is 0. Then the bending moment at X here is minus WX squared, which is this point here. And the bending moment at B is minus WL squared. So this one now will be a parabolic curve. It will be a parabolic curve, like it will be something like this. It will be a parabolic curve. So here is minus wx squared over 2, and here is minus wn squared over 2. Everything is, let us remove the minus, you know that everything here is negative. So this is the bending moment diagram.